Good evening, everyone. So welcome back to the Special Functions and Number Theory seminar. So we are resuming the seminar with our first talk by Michael Schlosser from University of Vienna, who will be talking on asymptotic formulas for the Fourier coefficients.
Good evening, everyone.
So welcome.
Yes. Okay. Thank you very much for the introduction. It is a pleasure for me to be the first speaker here in this for this academic year. It's a feel greatly honored. And I chose a topic which, for a certain reason, because I want to focus on actually finishing this work finally with my co-author, Myung-Hong Zhao, who is badly waiting and really needs that we want to finish this. And he's the expert on this topic. So I'm not really an expert on asymptotics, but I'm a learner. I'm very grateful that he invited me to join his project. And for more technical questions, I'm happy that Myung-Hong Zhao is in the audience, so you could maybe ask him then in the end. But let me present the my talk now. So this is on asymptotic formulas for the Fourier coefficients of infinite Q products. Let me see if I can change. Yeah, here. So first I will start with some background examples, motivation. Then I will show you the actual result, but I'm just giving you a flavor of it. I'm not giving you all the details. So there will be some constants involved which can be computed in principle and which we are for which we have formulas in our paper, but I'm just giving you the flavor of the result we have, because it would be anyway too much to present in a talk. And we will use our result to attack certain existing conjectures, and we're also able to prove new ones. And having more insight because of this powerful asymptotic expansion, we are also able to make new conjectures. Yeah. Okay, so the conjectures by Berkovich and Garvin so all of these will be settled in an asymptotic sense. They will be either proved or even refuted. So we will look at the results by Berkovich and Garvin, actually conjectures by Seo and Yi, and by Chen and Jeselwood. Do you understand me properly? Am I speaking clear enough?
It's clear. Yes.
Okay. Too quick, or is it fine? Okay, so maybe I just continue. Please feel free to interrupt me at any time. Okay, so we'll work in the setting of Q series as we'll look at expansions in Q, but because we're interested in modularity also in this context, we often view Q series as a function of tau, where Q is e to 2 pi I tau. And for Q being less than 1 in absolute value, we need the imaginary part of tau to be positive. Anyway, so this is our notation. This is the standard notation for Q-shifted factorials, AQ sub n, a product of n factors, 1 minus A, 1 minus AQ, and so on, and AQ sub infinity. So we will look at infinite products, and we will expand them in terms of Q. Then, because we will have sometimes several such products involved, we will put them into one pair of parentheses using this standard condensed notation, A1 up to AM Q sub n. Okay. Now this is already, so this was quite clear for most of you, I believe. Now what is particular to this work is that we will consider weight sequences, W, which are not just which are not just integers, but they can be any finite sequence. These are finite sequences of real numbers, and we will repeat them essentially. So they will have period t. So we'll have W1 to WT, and WT plus 1 to W2t will essentially the same sequence, and that will repeat, and so on. And we want yes. And for tech, and also maybe it's better to look at what we're going after. So assume that the weights are all 1. So if t is 1 and the weights are 1, then look at this generating function here, GW of q. This would then be just nothing else than 1 over q semicolon q sub infinity, which is the generating function for partitions. But what we're doing now is that we're modifying that or extending that by allowing arbitrary weight sequences. And we will call these coefficients appearing in this expansion weighted partition numbers. So they generalize the usual partition numbers Pn, which were studied by McMahon, Ramanujan, Hardy, and so on. And they have wonderful modular properties. In this case, we sometimes have modularity. We will point it out. So especially if we have some symmetries involved. Now, a technical thing, there's something written here about the GCT. That just means that, for instance, if let's say t is even, and the j's which appear in this expansion, which where the wj's are not 0, if only such would appear, then we would have an even series. We could essentially replace q squared by q. And for technical reasons, we want the GCT of this of the j's which appear with non-zero weight sequence weight value together with the t to be co-prime. Okay. Anyway, so here's a kind of a justification also how we can consider this to be weighted partition numbers. So expanding this product by a, let's say, multinomial theorem, but convolution, or actually a convolution of the binomial theorem simply, we get an explicit formula for the PW of n in terms of partitions. And for each partition, we have this weight here appearing. So if the wj's are all 1, this will be just 1 sub mj, which is mj factorial, and this will cancel. So this will be just 1. So we'll count every term once. So every summand will be weighted once in every partition. But now we have certain weights for the partition. So these will be the weights we have. And they will be real numbers. Okay. And we are interested in asymptotics as n goes to infinity. So here we use the q, not the q shifted factorial, but the ordinary shifted factorial notation, or the Hochhammer symbol. Here on the bottom line, we just say that we want the wj's, the weight sequence to periodically extend, to repeat periodically with period t. Okay, I think the model is quite clear. And as I said, we want to let n goes to infinity and ask what does PWN approach to, and maybe maybe more information is even possible. Maybe we can even get an asymptotic series for that. Okay, so first look at important cases. So if the weights are all 1, so we just need period t1, the modulus is 1, everything repeats. We just have the generating function of the partition function p of n. And more than 100 years ago, Hardy and Ramanujan proved this as some famous asymptotic formula for p of n. And to find this, they introduced the circle method. So they introduced the method, a powerful tool. The difficulty is that we have infinitely many poles in this series, but they repeat. And the poles are exactly at the roots of unity. And that's why, so think of circle method in connection with roots of unity. So that is what they needed to get to this result. They actually used the modulus symmetry of the Dedekind eta function. And this is the Dedekind eta function. So it's a function in tau. It's essentially 1 over this function. It's yeah, okay. It's a modular form, but I don't want to be too theoretic now. You will see a lot of theory involved, but I will try to just give you a flavor of the results. So Rademacher later, when he was coming from Germany to United States, I believe, I'm not sure if it was still in Germany, but in 1943, he expanded this work of Hardy and Ramanujan and gave a more precise result, namely a complete convergence series. So PFN is this series. So it is quite exact and it involves derivatives here. N, okay, so one takes the formal derivative of n, but of course one could replace this n appearing here by x and saying you take the derivative with respect to x and then in the end we replace x by n. Okay, so this is an expansion which involves these omegas here and their Schlosser sums. They involve actually exponentials of actually Dedekind sums here, SHK, and they themselves involve Bernoulli polynomials of the, well, just the first polynomial. Here, with argument j over k, there's at a rational point, and here at well, there's the fractional part of a real number here, also of yeah. But anyway, so this is quite interesting. But of course, though, there's a very arcs and there are different things involved in this. I will not go into too much detail to just give you a flavor that there's a lot of theory involved. Maybe just point out that from a modular point of view, the case where the weights Wj satisfy the symmetry, Wj yeah, equals Wt minus j, kind of modular symmetry, as you have in the, let's say, in the product belonging to the Rogers-Ramanujan continued fraction, for instance, or just the Rogers-Ramanujan functions. So you have this type of symmetry there. In that case, this generating function GW of Q, I just want to recall it one more time what it is. It is this function. So just remember that this GW of Q is nothing else than this generalized generating function for partitions, where we have weighted partition numbers in the expansion. So if the W of the weight sequence satisfies this modulus symmetry, then actually this is a modular type of product. Okay, this can be expressed in terms of a so-called Klein form and certain quantities appearing here. Here in the exponent of Q, there appears now the second Bernoulli polynomial. Okay, so this is just a little bit to show off. I agree, this is not, but we will not need this for the talk. Still, I'm giving a reference here. So if you're a bit confused and want to know more about what Klein form means, you can look it up in chapter 2 of Hubert and Lang's famous book from 1981 on modular units. Okay. Okay, so there's in these cases we can give we have nice formulas, and actually we have also periodicity of the coefficients in Q. If we think of just a sign behavior, in terms of sign behavior, there is a certain kind of periodicity involved. In other cases, the situation is much more complicated. So we will be concerned in the further remaining of the talk with situations where either we have modular type of products or we do not have this situation. But we may have other things instead. Okay, so what Rademacher did, he extended a certain method of Hardy and Ramanujan and gave a more exact formula, and actually even a asymptotic series for PW for P of n. And we are able to do the same essentially for PW of n. This is actually quite well known that this can be done. And as I said, one can use it either to prove the asymptotic, not just the growth of the coefficients, but also maybe the periodicity of the sign. So the coefficients so in absolute value, they might grow the coefficients, but the sign might change periodically, as this is in the case of many famous conjectures and established results. Also in the coefficients in the Q-series expansion of the Rogers-Ramanujan continued fraction or the Greenwich-Gordon continued fraction, it's well known that the coefficients are periodic with periodicity 5 or 8 in the later case. So many cases, so for special weight sequences W of modular type now have been investigated by independent researchers like Iseki, Lehner, Livingood, and so on. And also in joint work with Yunhong Zhao, we looked at expansions related to the infinite Borwein product. And some of our conjectures have been solved by Brinkman, and Kane recently. Anyway, also Shane Cherner should mention as a recent contributor to this deep subject. Okay, so now I want to give you the asymptotic expansion, and just that you have the flavor of the results. So we will work with multi-valued functions. Sometimes we have to make them single-valued by fixing, let's say, the branch of the logarithm or taking the principal value for these multi-valued functions. So usually so these are just technical things known to experts. As you know, with the square root, there are two solutions, and we also fix the solution with a square root, with a real part of the square root of a number is non-negative. Many special functions. So this is a seminar on number theory and special functions. So I just throw a few special functions to you or in front of you, just that you see what ingredients are involved. The dilogarithm function will be involved in a modified Bessel function of the first kind, either is defined in this way or by an integral representation, gamma function, and many more functions are involved. Okay. So now, to be more concrete now on the method, so that will involve actually a careful saddle point analysis, but there will be many points of interest where we have steepest descent, essentially. So the points of interest where we select from will be from this set of reduced fractions in 0, 1. So it's enough to look at 0, 1 because things essentially repeat. And we'll have this curly Q of T, which is a set of H over Q, where we cancel common factors, where H is less than K and K is a divisor of T. So we'll only take those. And then we will also consider averaged sums. So here we have a certain sum with T summands, and we divide by T. So that's an average sum involving this Dye logarithm here, this Li2 of U, I'm sorry, at certain points. So we'll take those. And there's a technical assumption here, which just means that there is at least one element. So there's at least one theta. So this will be evaluated at different points of theta in this set Q of T of this particular reduced fractions. And at least one of them will be not on the half line of the complex, on the negative real line of the complex plane. Okay. Anyway, and of course we want the argument to be, of course, let me just go back. We want the arguments to be chosen properly here. So we'll have a problem otherwise. Is that true what I'm saying? Yes. Yes, that is the case. But anyway, let me just go further. It's maybe already too detailed what I'm talking about. And then we will, so these will be a certain points which we will evaluate. We will look at the alpha w's. Then we'll take the square root, which is also well defined, and take the real part, which is non-negative now, and take the maximum value. That will be kappa of w. And then there will be possibly, and this makes it interesting and complicated, there will be, so this is where the dominant terms are in the, let's say, which determine the asymptotics. But that could happen at several points. So the different thetas were of this curly Q of T, where this maximum is actually obtained. That will be the set SW. Okay. Now let me show you the result. Okay, so our result says that there is a real constant for each. Yeah, so we're looking at PW of n. We want to let n go to infinity. We're looking at the asymptotics. We not only have a result for n going to infinity, but actually a full asymptotic expansion. It is determined by a sum where we, over all these thetas in S of W, which determine, like, say, the asymptotics. So it's just now a finite sum, actually. And take the real part here. So here is still a PW of theta and n involved. This will be a asymptotic series. And here, so this is now a finite sum of asymptotic series. And here, this is a error, which is bounded and which we can quite exactly determine. It involves theta, the kappa of W and the theta. And the theta depends only on W. And the asymptotic expansion is now a series where L greater or equal to 0. So it can be truncated, or it can be just go to infinity. It involves now this modified Bessel functions and certain constants evaluated at other constants. And also, I should say, what I'm now hiding is that, yeah, and this asymptotic expansion is with respect to this asymptotic sequence. Okay, so with otherwise the series can be compared to that one, which converges. which is asymptotic, yeah. Yeah. Sorry, this is so it's with respect to those points. But anyway, the constants involved, they are complicated, but they are computable, and they involve they depend on W, L, and theta. And they involve sums of variations of very special functions, which I showed you, and also involving trigonometric functions and so on. So it would be too much to present those as well. And also, I should say this work is not published yet. So that's maybe another reason I'm not showing you the full results at this moment. Any questions on this now? If not, then yeah. So okay. So now let just continue. I hope you can still hear me well, and you're still with me. Yeah. Okay. Okay. So the difficulty now. Okay. So we have a formula. We have maybe several asymptotic sums appearing there. We have an error. We have a bound for the error. And what is the difficulty is now for each W to effectively compute these constants appearing. Where I have not shown you how complicated they are, but they can be computed. And they are actually real numbers. So they're gamma, W, mu. And one can do that to compute the Fourier coefficients, let's say Taylor coefficients in cube, or Fourier coefficients in tau of GW of Q for any of these cases which are determined by these periodic weight sequences W. And we can also essentially multiply the whole expression by a polynomial in Q, also with unit roots of unity appearing as poles or the zeros, not really, yeah. So it's up to some extra factors. We have essentially G of W, but sometimes this appears in applications that we have something slightly contiguous to the full product. But anyway, so we can also use the formula which we have to give asymptotics of such products. Okay. And we can use it to either settle existing conjectures or to prove new results, and even more, because we have now more insight. And and together with computer experiments, we're even led to formulate new conjectures. Okay, and I will show you a few of them. Okay. So first we look at a well-known conjecture by Berkovich and Garvin. So motivated by Saito's conjecture of 2003 on non-negative eta products, Berkovich and Garvin, they formulated these two elegant conjectures in 2008. So they're quite nice, and they actually don't look too hard. But the difficulty here is that the generating functions depend on several parameters, and A, B, M, and N. So there are infinitely many parameters. So if there would be just one case, so in each finite case, one can certainly use existing, it's not difficult to apply methods, and I'm sure that conjectures would have been solved. But this is actually true for any sequence. So this was the conjecture, and then there's the other one, which is a quotient of two infinite products here. So here we have in Q to the A and Q to the B. So it's not modular, but but there's still a nice symmetry in A and B. And here there's just a Q of A here, and the A should be the 1 or 2 in the second case. So we call the coefficients in this expansion P, BG of 1, here P, BG of 2. P, BG 2. Okay. So they proved that these are all non-negative, these coefficients in these cases. Actually, they conjectured this, sorry, they conjectured this. And we want to see if this is correct. And it's clear that the framework of our setting applies. So this can be indeed written as in terms of GW of Q with certain weight sequence W. And what we have now is this case. It's just a asymptotic result, so we don't have the full proof that from a certain coefficient L on, which depends on in each of the cases on the parameters involved. First case on A, B, M, N, and N, and the second case of A, M, and N, we indeed have non-negativity. Okay, so this is maybe what could have been expected. So, and there would be infinitely, so for each fixed set of parameters, of course, one has only finitely many cases to determine. And but the problem is that here we have to prove the full conjecture, one would need to show infinitely many cases. So the full conjecture here is still by Berkovich and Darwin is still open. And they are yes, so I forgot now how large these constants are, but they are principally in small cases of the parameters, it's in reach for the computer that one can settle it full, but for large ones, it grows, of course, quickly. Okay.
Michael?
Yes?
So for specific values of A, B, M, N, these would constitute some known special cases, right? So there will be combinatorial interpretation of...
yes, they are combinatorial interpretation for these. Yes, yeah.
In general, it would be somewhat complicated, I guess.
Yes, I'm not sure now. I forgot now if there is a combinatorial interpretation. No, there is no. If there would be a combinatorial interpretation in general, then that would solve the conjecture of non-negativity. Yeah. So that would be, of course, even better to have a combinatorial interpretation. Yeah.
Right.
Okay. Let me continue now with the conjectures of C and E. They're more complicated to attack. So that was more recent. So 2020, Myers and Myers, they introduced a new statistic for petitions called the index of petition, arising in the context of so-called seaweed V-algebras of type A. And I think, if I remember correctly, that is connected to the M equals 4 case, I think, of what is done here. So Seung-Yi studied maybe 2 or 4, I'm not sure, but anyway, so small case for small m. And Seung-Yi in 2020, they introduced the extra parameter m and looked at this generating function. So this, again, I can say already now, this falls into our framework of GW. But anyway, so what Seung-Yi conjectured, for any m greater or equal to 4, the coefficients appearing this expansion would be non-negative. Yeah, so actually the Myers and Myers conjecture, I think, or statistic concerns the m equals 4 case. So only from m equals 4 on, one has this non-negativity. So that is what is conjectured, but also for larger m, this is what Seung-Yi conjectured. And they conjectured even more, like a certain relation between the coefficients. that there exists a positive integer n, which depends on m, so that from a certain n on, and fixing the m now, the coefficients are not only positive, but they grow. But with these distances at m, so there's a periodic behavior of growth. So looking at the m dissection, there would be a growth. Okay. So it's not that it's clearly grows and completely. So they jump, they go up and down, but oscillate, but growingly oscillate. But there's a kind of periodic behavior which they noticed, and they formulate this conjecture. Okay. Yes, actually, the m equals 4 case is equivalent to the conjecture of Myers and Myers. Okay, so that's what they did. And this actually was settled asymptotically by Chern recently using the circle method and the Mellin transform for certain n, which is quite large. So it's quite clear why it's not a foolproof of that case. But actually, not much later, so Craig used also the circle method and the Euler-Maclaurin summation formula to prove the Bose-Myers conjecture for all n with a much lower bound, so 35,000. And I forgot now if the other cases have been settled by the computer, or if it's still too complicated, or if no one has done that. So that is maybe a question I would have on to Newnham later, maybe. But anyway, let's look at the general case for general M. So this product by CO, considered by CO and D, can be written in such a form, and one can see easily that this falls into our framework. So this is a GW of Q product as we defined it before. So we can apply our asymptotic result to this, and we're actually able to partially prove CO and D's conjecture. And actually, we also we refute it in some case. So I will show you here. So this is our result. So asymptotically, for a certain large, let's say, constant, which depends on m, we can prove the non-negativity, the non-negativity of the coefficients. So they are all equal to 0 from that L on. And then actually there is a behavior like what's it called, a periodic pattern, but of the coefficients rising, but as far as if I'm correct, wait a moment. Yes, I hope I formulated correctly. But they would, yeah, they increase. Wait a moment, is this correct? I have to check that with Newnham then later. Here I say that they increase for all even m and they decrease for all odd m. Yes. Can that be if they're integers, the coefficients? Yes. Okay, so our conclusion, I should check that, is that actually the second part of the conjecture by CU is true for even m, but actually false for odd m. Yeah. Okay, so maybe it can be correct. There's an inequality here, but anyway, okay. This I have to check, but I think it's probably written correctly as here. Maybe there's some misconception from my side now. Okay. Okay, so here so as I mentioned before, we're able to give more results or actually conjectures. Here's some conjecture now involving real numbers in addition. So we introduce an x and y here. So instead of having just q and minus q to the a minus 1, we can actually multiply this by x and y here and have x and y in certain regions. So this is a region in R2 and this is another region. And we still have non-negative coefficient. So this was observed. That's maybe interesting. Of course, it's maybe more. So here our methods do not apply here because the poles here are not anymore roots of unity. So it's a bit more complicated, but they still have some periodic behavior. But still, also because x and y, they're infinitely many, one needs new methods here. So one needs some kind of, maybe taking dominance or something like that would be needed. But anyway, let's continue. We have another conjecture, which is related to the m equals 4 case, but extends it in another direction. So the coefficients in this expansion are non-negative for a certain d equal. So see here that there's a minus here. So this case, only with this factor, everything would be, of course, non-negative, but we have a plus here in this other infinite product, which is similar to what we have here, different signs. But here we have squares involved. So that's quite interesting. And d should be here either 1, 2, 4, 8, or larger than 8. So 9, 10, and so on. And the coefficients are negative. So for 1 and 2, it's true. So for 1, it's easy. For 2, it's also true. I think not just asymptotically. Yes, and for d equals 4 and larger, and 8 and larger, we need new techniques. Probably more than the circle method. Okay. Everything fine up to here. Then I will go to the last section. We will look at the conjectures by Chen and Wieselwirth. They're quite old, actually. And this is connected to considerations of modulo type products, but for which we have very nice results. But and there are some products which are not modular, but still similarly have nice properties. And I will show you what I mean by that. So remember, modular type products concern weight functions having this property for fixed t, modulus t. Wt is Wt minus j. And Richmond and Shekaris already gave, for instance, a asymptotic formula for the Rogers-Ramanujan continued fraction modulo 5. So this is the famous Rogers-Ramanujan continued fraction. So this is one Ramanujan function divided by another. And it has a very nice continued fraction found by Ramanujan, which is specialized at certain points, which involved rational, or let's say, expressions to radicals, so which was quite impressive then. And so Richmond and Shekaris, they applied asymptotic analysis to get this result. So as n goes to infinity, one has this, and one can actually read off the periodicity of the signs here. So here cosine 2 pi over 5 n minus 2 over 5 is involved, and there's a certain sign. So this is either positive or negative, and with period 5 the signs repeat here. There are similar results for the Gremlin-Gordon continued fraction and for other similar products. So this is a typical result. The Gremlin-Gordon one is very similar. And this has been studied by various authors involving, including Andrews, Bersout, Aladi and Gordon, Chan and Gates-Lurt. And sometimes a lot of Q-series machinery is involved and theta functions. Another question would be, what about other continued fractions? So these are still nice infinite products, but maybe those which are not necessarily modular. For instance, the modulus 3 continued fraction by Ramanujan. So here it is. So this is not a modular product. So here's the Q square. The modulus is 3 here, but they do not appear on the same side, let's say, but with one is in the denominator, one in the numerator. So this is not modular, but it still is nice in the sense that it has a very nice continued fraction. So what about the Q series? What about the sign behavior of this series, for instance, or of the reciprocal here? This is not a mistake here. So you see here this always looks the same, the two continued fractions, but here the minus appears down here. Here it's there, and there's a relation between the two series, between 1 and 1 over the series. So yeah. Anyway, so Chan and Yates-Lurt looked at the asymptotics and using the computer, they made the following conjecture. So there is a kind of periodicity in the sign change or in the sign pattern, but it's not stable. So there are intervals. There's an interval where there is a periodicity, and then it changes, and then there's again a periodicity, then it again repeats, and then there's again a change. So somehow, yeah, so it's not a complete periodicity. And the intervals for which one has periods, they observed that, or they conjectured that they would increase, but from a certain index on n greater or equal to 63. Yes, and there's a second conjecture, and I think it's quite similar. And yes, and I think this is almost the same, but it's for any n, not necessarily greater than 63 here. Yeah. Okay, so that's this other conjecture we have. Okay, so with our methods, of our new methods, we are able to attack this too, because this appears this is clearly a product of the type GW of Q. And we have these asymptotic results. So asymptotic formulas, but we have more than that. So for the coefficients in the first expansion. So here the modulus 3 Rogers-Ramanujan, not Rogers, the modulus 3 Ramanujan continued fraction, and here's the inverse of that. And here are the coefficients, the PRF of the PRF3, PIRF3. We have formulas as n goes to infinity. So cosine appears, certain constants appear. K, for instance, K3 is this sum. It's maybe not so surprising for experts why such sums appear, but anyway, this can be computed to any precision. It's not really a problem. So K3 appears here. We have square roots involved with pi, we have other powers. And we have a cosine involved, involving pi, which is okay with the cosine, but also involving the K3 and square roots of that and square roots of other things. And also the square roots involve some delta, and delta is also some constant. So it's just here. Yeah. And of course, this is a bit complicated to see what the sign pattern is of this sequence. So the sign pattern of this, which is non-negative, is actually determined by the sign pattern of cosine of this. And that's a difficult question. And here we have some extra constant, appearing n minus 1 times some extra, actually a bounded function depending on n, which I'm not showing you in detail here. Okay. So this is one result, and now we're looking at this bounded functions. So actually so my claim was, of course, that the sign depends on cosine, and the question is if this is really true or not. But so we actually have two terms. So it's not clear that this would be here the sign would only depend on that. We also have this here. And actually I'm sorry, so it's not quite true that this is non-negative. This actually oscillates also, or actually it's positive and negative, and here are the values of these series. So it looks like that they're bounded at least. So the size we can bound it. We have approximate bounds for the coefficients for the symptotics here, because this is anyway bounded, and the cosine, and this is bounded, but the sign is still complicated. So what about the sign? So this does not help so much yet. So because this is still complicated, as you see, and this is just plotting the function. So we see how it looks like. And we have looked at it for values of n between 1 and 2,400. Yeah. Okay. And now we can get a by more work, we can get a more precise result, namely that there's some plotics for in both of the cases. So in I equals 1, or sorry, what was it? Wait a moment. In both cases, so it depends now on fr of a and fi of a. So let me see. So we have two polynomials, and I think they're different depending on the cases. If we are in the first or in the second case, we have this maybe more precise asymptotic expansion. This is now, so now we're after the coefficients, so to see the sign pattern, and we have, maybe let me check here. So this is quite complicated. So there are irrational numbers here involved, appearing as to be evaluated at cosine. But here, what we managed to do here, to say this is just the O of n minus a. So this was what the work achieved. So instead of having this something oscillating here, we're able to get rid of that and now have a formula which depends only on whose sign is determined only by the cosine of this here. But this is quite complicated, and it's also not even clear if this vanishes or not. So this could vanish. It's maybe similarly difficult as the conjecture for the tau function, if that vanishes or not. So that's maybe similar. So it's not quite clear if this would ever vanish, but we have a conjecture that asymptotically the growth is determined in such a way, logarithmic growth. So it goes to a constant in both of the cases. And yeah, and of course, and that indeed asymptotically the coefficients that actually they grow and grow, and they actually will not be zero. That's our conjecture. So this is on the infimum, so that's why the coefficients they will not go to zero. So the infimum will go to infinity. Okay. So actually from a point, yeah, okay. Yes. So if there is a zero, then that should appear, let's say, early, and it will not be infinitely many times zero. But anyway, let's continue. So this is a quite strong conjecture. We are not able to prove that actually. So this is just based on computer experiments. And as I said, yeah, we actually believe that the coefficients never vanish from a certain point on, from a fixed point on. That's what and even that we cannot prove. But what we can do, and this is a theorem, so this is not a conjecture, that the first part of the Chan-Jeselwood conjecture is false. So it is not true that, although it is quite plausible that this could be the case, that the intervals where the chronicity occurs would increase always, yeah. So this is not true. And but the second part is true for sufficiently large integers. So there's so periodically things work. Yes, yes. So periodically one has yeah, there was a kind of maybe it's a bit too long ago. The second one was that looking at the third coefficients here for j equals 0 and 1, the intervals have increasing length. So that is appears to be correct, but not in, yeah, but the first part is not. Yeah, so I think I'm just completed in time. So thank you very much for your attention. And I'm happy to hear comments and questions.
Yeah, thanks, Michael. Any questions? So, Michael, I had one question. So we have
Yes.
one result that you showed where you had square partitions.
Yes. Shall I go there?
Can it be extended for power partitions, like kth powers?
That I think we might have looked at that, but I'm not sure now. My naive guess would be that maybe for instead of 2, maybe having 4, one could think of something.
Okay.
But not, I think, but I think not. Yeah. But anyway, it's just one. Yeah. Yeah. We have not tried to find all kinds of conjectures, just that, yeah, this is just one
Okay.
of the things we considered. Yeah. which seems to be beyond what we are able to do. So yeah, so see that here because of the squares, we don't have this periodicity anymore because yeah, let's click here. Yeah, this is quite interesting.
Yeah. Any other questions?
Could you check the chat box?
Okay, hi. Anyone said something?
Oh, I think Abdul Hafiz has put something in chat. I suspect K3 can also.
Okay, Abdul Hafiz. Yes, I think he's traveling at the moment, so he might not be able to. Okay, yes. So, okay, he said that he's proposing a formula. Yes, that might be the case. So I'm not so much familiar with the trigamma function, but you're pretty. He's asking if K3, which appeared as one of the constants of interest here, he said you observed or asking like it can be written as 2/9 square root of 3 times 3 gamma of 1/3 minus 3 gamma of 2/3, and I'm pretty sure he's right. Yes, so yeah. You may please Abdul Hafiz, please email me that maybe it's a typo. You said a typo anywhere.
Yeah.
Please, yeah, if it's correct, please email me that so I can maybe yeah.
Any other questions? So if not, let's thank Michael for a nice talk.
Thank you, Michael, for starting the season in a nice way.
Yeah.